right, good afternoon and welcome everyone to today's webinar. My name is David Godwin and I'm the coordinator for the Southern Fire Exchange with the University of Florida. Today I'm excited to introduce our guests, Dr. Talat Odman and Dr. Fernando Garcia Menendez, as they'll be speaking about the SIPFIS Prescribed Fire Tracking System. Having coordinated several years of surveys of prescribed fire practitioners, land managers, researchers, and air quality specialists, I can tell you, and many of you know, that having a unified system to track and quantify the impacts of prescribed fire on air quality has been a regional need for quite some time, particularly in the Southeast where we have so much fire. So I'm glad to have these researchers sharing their work with us today, and I hope that you will stick around for their demonstration of the system that they've been working on. I would like to take just a moment to share a little bit of information about the Southern Fire Exchange, our program. SFE is a regional program for fire science delivery in the Southeast. We're a collaborative between the University of Florida, Tall Timbers Research Station, and North Carolina State University. We work to develop programs, opportunities, and events that bridge the divide between the fire science and wildland fire and natural resource management communities. Throughout the South, we host workshops, we coordinate webinars like this one, develop fact sheets, and create other content to move science into the hands of managers. We also work to connect researchers with the pressing and relevant needs of the management community. The best way to stay connected with us and to receive notifications about our upcoming webinars, field tours, and other products is to join our email list or to check out our website at southernfireexchange.org, which is where you can sign up for that. Or you can follow us on Twitter or Facebook. And finally, if you're joining us today from an area outside of the Southeastern U.S., first of all, welcome. Glad to have you with us. And please look into connecting with your local Joint Fire Science Program, Fire Science Exchange Network. Just like us, these are the folks that are working to connect regional managers and researchers to address local fire science issues and ultimately make a difference on the ground. So you can visit firescience.gov. You'll find a map just like you see on the screen, and you'll be able to click on that map to connect with your local exchange network. And now it's my pleasure to introduce our speakers today. Dr. Odman received his PhD in mechanical engineering from Carnegie Mellon University in 1992. With a thesis on the modeling of long-range transport and fate of air pollutants emitted from urban areas. After graduation, as a research scientist at North Carolina Supercomputing Center, he contributed to the development of the Community Multiscale Air Quality Model, CMAQ. In 1997, he joined Georgia Institute of Technology, Georgia Tech, where his research focused on determining the causes of regional haze. And since 2007, his primary interest has been wildland fires and their air quality and health impacts. He developed models to improve the representation of fire plumes in air quality simulations and incorporated them in air quality forecasting systems. And the system that he's developed is operational and will be highlighted in this presentation today. We'll also be hearing from Dr. Fernando Garcia Menendez. Dr. Menendez is an assistant professor in the Department of Civil, Construction, and Environmental Engineering at North Carolina State University. He received his PhD in environmental engineering from the Georgia Institute of Technology. He completed his MS at Stanford University and BS at Tecnológico de Monterrey in Mexico. Prior to joining NC State, he was a postdoc at the Center for Global Change Science at the Massachusetts Institute of Technology, MIT. Dr. Garcia Menendez's research focuses on developing computational tools based on numerical models and methods, uncertainty analysis, and integrated assessment modeling to simulate interactions between environmental and human systems. His current interests include wildland fire and air pollution, climate change impact projections, computational methods for environmental modeling, and air quality in Latin America. So welcome Talat and Fernando.
Well, good afternoon, everyone. It's really a pleasure for me and Fernando to speak to you all about the Southern Integrated Prescribed Fire Information System that we were developing. I want to start by thanking those who shared their prescribed fire data with us. And I hope that those of you who haven't done so yet, after seeing what we can do with your data, you'll decide to share it with us. We still have time to incorporate your data into the system. And also, there is room for some changes in the system. So if you have any comments, please send them to me or to Fernando. So as most of you know, prescribed fire is a favorite land management tool. It's used to improve the ecosystem and also reduce the wildfire risk. Now, we hear more about wildfires than prescribed fires, at least in the media, but about half of all wildland fire PM 2.5 emissions, particulate matter of size less than 2.5 micrometers, they're all attributed to prescribed fire. So it's about half and half in the US. And a recent study has shown that 40% of Americans are living in places with some kind of moderate or high contribution of fire smoke to ambient PM 2.5 concentrations. And we also know that wildland fire smoke, and especially PM 2.5, as well as other constituents in the smoke, lead to negative health effects that range, from asthma to heart attacks to low of birth rate, and also to premature mortality. Now, this map is showing us that most of the prescribed burning activity south. And if you look at the bar charts, you can compare how much of the total acres burned in the nation are from the US and how much of it is from the other states. So here, the definition of the South includes Texas, Oklahoma, Arkansas, and Louisiana. And you can also see that the numbers are increasing over the years. So we are burning more and more. But some of the numbers, especially what I state at the title of the slide here, pertains to Southeastern U.S. That doesn't include those 4 states that I just named. So the #1 source of PM 2.5 emissions in the Southeastern U.S. is prescribed fire. And this is according to the 2014 National Emissions Inventory. So our project is funded by the Joint Fire Science Program. You can see the project number there, and there's a live link on the registration page that will take you directly to the Joint Fire Science website and to our project, the abstract of the project. The objective is to develop an integrated prescribed fire and air quality information system for the South. And the following statement is from the proposal. So the system will comprise prescribed fire and air quality data and results from model simulations conducted to address questions regarding the impacts of prescribed burning on air quality, smoke exposure, and associated health effects. And you'll see today that we have been making progress on many of these fronts. Now we have envisioned SIPFIS as a layered system. So at the very bottom, we have a layer with the prescribed fire data. So we would be overlaying the air quality data on top of that. And then we'll continue adding layers of smoke exposure, population data, and finally the health impacts. And as David stated at the opening, it's really not, we found this the hard way, that it's not easy to compile prescribed fire data for many reasons. There are a large number of small fires, and you're seeing some numbers from Georgia there. The mean is 20 acres and the median is even smaller, 3 acres. And we know that the fires are short-lived, and these are low-intensity burns with smoke plumes that are not as large as those from wildfires. So if you try to detect prescribed burns from the satellites, for instance, all these factors are going to work against you. And of course, with remote sensing from satellites, you're not going to be able to discern wildfires from prescribed fires. And as David stated, there's no unified record of prescribed fire data. So in our work, we relied on two sources of prescribed fire data. There are some satellite-based records with some acronyms there. I'm gonna come back to the BBEP acronym, so let me spell it out. It stands for the Biomass Burning Emission Product. It's by NOAA. So the characteristics of these records are that they are consistent over space and time, and they're regularly updated. So this is a plus. But the minuses are that they fail to detect many burns. And as I mentioned before, they cannot differentiate prescribed and wildfires. And there are significant uncertainties in fire size and timing. For instance, some satellites, the overpass of the satellites may be outside the span of a burn. So in that case, the fires are undetected, and also they may be so small that the resolution of the satellites cannot see them. The second set of records that we relied on are permit-based. And the advantage of this type of records is that they register a large number of prescribed fires, small and large. But the minuses are, there are inconsistencies between how different states and agencies keep these records. And some states, may not even have any records. So you will not have this type of data everywhere and all the time. And another disadvantage is that the states that we know of, they don't go back and check whether the permits were executed, or whether acres that are recorded on the permits were burned or not. So this is an uncertainty in fire size, timing, and occurrence. So recently we have published a paper on this where we compared the burn area between permit records and 2 different satellite-derived products. This appeared in the Journal of Geophysical Research back in March, I believe. So if you go read this article, there are some estimates of the uncertainty, both for the permit records, for which we ran a phone survey. So we actually called the burners and asked them if they really burned as many acres as they said they would on such and such date. So that allowed us to put an uncertainty bound on the permit records in terms of the burned areas. And this slide is showing the uncertainty in the satellite detected burned areas. On the y-axis, we have the BBEP product, the acres from the BBEP product, and on the x-axis, we have the burned permit acres, and this is for Georgia, both for 2015 on the left and 2016 on the right. Now, each one of the points is a daily total in the state. So in 2015, all of the days, the satellite was low compared to the permit totals. In 2016, on some days, the satellites were high. We don't know what the reason for this change in behavior of the satellite data is. But nevertheless, for both years, you can see that the satellites are severely underestimating the total burn areas. And the situation is the same for Florida, for instance. So it's not just for Georgia. Now, in the next slide, I'm gonna take a look at this point right here, a day when the satellite total burn acres agreed perfectly with the total from the permit records. So unfortunately, when we look at the detail of that day, we see that there is no agreement between where the permits are and where the satellite detects the fires. So the yellow dots are the permit records here. The green dots are the fires detected by the satellite. And also the size does not agree. For instance, we have a very large fire here, right here. And this is because the satellites don't have sufficient resolution to detect the small fires, and likely it sees a cluster of small fires and interprets or misinterprets it as one big fire. And when we do the based on the county totals, you can see that the satellites don't see any burns in these counties where there were some permits issued. And actually, this is the county where the satellite placed the large burn that it thought it detected. So at this point, I'm gonna hand the microphone over to Fernando, and he's gonna talk to you about his analysis of the data that we have collected so far.
Okay, thank you, Talat, and thank you to everyone else who's joined the seminar. It's great to have a chance to speak to you. So as Talat said, I'm just gonna talk a bit about the prescribed fire data that we have been using and go into a bit more detail looking at these specific data sets that we've been using. For the reasons Talat just described, we decided initially to focus on permit-based prescribed fire data and started collecting permits for southern states. So for the records that we have collected, it was necessary to systemize them because the data can vary widely across different records. So for example, from the data we receive, some of the data can be organized into county totals. In other instances, we have data that's actually data for individual fires. That's a big difference. And also the formats of the different data sets and the data fields captured by different agencies or different groups collecting prescribed fire data can be quite different. So for example, if we compare data sets or different sources of data that we got from different states, in this case, North Carolina, Georgia, and Florida, the format of the spatial information can be very different. In some cases, we get data with geographic coordinates, but in other occasions, we only get an address associated with prescribed fire permits. And that address information can have varying levels of detail within them. Some of them can be very precise. Sometimes it's not very precise address information for the burns. Sometimes we have shape files instead of an address or coordinates. And there are also differences in the temporal resolution or the temporal features included in these data sets, and the level of detail pertaining to the fires recorded in each data set can also differ. So sometimes we have just information about acreage burned, a date, and an address for the fire, but sometimes there's data sets that include additional information about fire type or specific fuel types that were associated with different burns. So we've been systemizing this permit data from different agencies to try to use it in the information system that we'll talk about a little later. All right, and in the next slide, we have the data that we have been able to collect as we've been working on this project for prescribed fire permits. And we've been able to get some data for Florida, Georgia, North Carolina, Tennessee, Mississippi, and also data from the Tall Timbers Research Station for multiple years. As I mentioned, the data fields and the data formats can vary. So we've been trying to systemize these and work with different types of data in an integrated fashion. I'll just quickly mention, and we'll mention throughout the talk maybe multiple times, that we'd really appreciate any additional data that can be shared, especially for new locations or for more recent years. If you're interested in sharing the data, we'd be happy to integrate it into this effort and be very thankful for any new data that can be shared with us. Okay, so I'll just describe kind of some additional details of what this data looks like and how it can be beneficial for this type of project, for this information system that we'll describe a bit later on. So we've been exploring the fire data within these permit-based records. And as I described before, or as Talat described before, even for these burn permit records, there are still significant uncertainties associated with this fire data. So one question we had initially was if this permit-based data can really serve the air quality related purposes that we had, or the impact assessment objectives that we had as part of this project. So we looked at the data that we have from these permit records and looked at air quality records from air pollution monitoring sites in the Southeast to try to answer this question. And what we've basically done is integrate permit-based fire data with air quality data and look at different sites in the Southeast and the amount of prescribed fire that is burning or is at least permitted around each of these sites. So for example, if we look at Albany, Georgia, you can identify trends in prescribed fire permits, which, as we might expect, increase each year during the burning season. Sometime around January through April, you get higher burning. And you can also see, if you look at air quality at these sites and the amount of permitted prescribed fire activity around these sites, that days with higher PM concentrations, at least in the Southeast here, and for PM 2.5 concentrations specifically, tend to correspond to days with prescribed fire activity occurring near the site and fairly close to the time of these PM observations. So for example, if we take a look at Florida and Georgia and the air quality monitoring stations located within these states, you would find that from the 2013 to 2016 during the fire season, over 90% of the days that had a relatively high PM 2.5, so that's above 15 micrograms per meter cubed, also had prescribed fire permitted near these sites. So in the vicinity of these sites, most days with higher PM also had significant prescribed fire permitted around them. And the days that had much higher PM 2.5, in this case, above 25 micrograms per meter cubed, had a significant amount of fire permitted near the site. So over 1,000, about 85% of those days, over 1,000 burn acres permitted near this site on the day of the PM 2.5 observation, or the previous day, the day prior to the observation. In the next slide, so one thing we have done is to look at the association between air quality, PM 2.5 specifically, and prescribed fire activity in Florida and Georgia using PM data from monitoring sites at these states and prescribed fire permits in the vicinity of these sites to get a better picture of the influence of prescribed fire on air quality. And in the next slide, what you see is that we find that at most air quality monitoring stations in Georgia and Florida, this includes, I believe, about 30 stations in Georgia and close to 50 in Florida, we see at most of them at least a significant correlation between measured 24-hour average PM 2.5 and prescribed fire permits or permitted prescribed fire occurring near these sites. And sometimes these can explain for different seasons or different sites, they can explain a fairly significant amount of the variance in burn season PM 2.5 concentrations, so up to 50% of the variance in some cases. That correlation is, of course, much stronger during burning months, 2 to 3 times stronger during the burning months than for the full year. It tends to also be higher in some locations, which are, as we might expect, closer to higher burn intensity and lower in urban areas, or some areas near coasts as well. In the next slide, as we might expect from the previous information that Talat presented, that association between PM 2.5 concentrations observed in the Southeast is stronger with, the association is stronger with burn data recorded in the fire permits than the data that we could derive from satellite detections. In this case, if we compare prescribed fire burn permits and their association with PM 2.5 to that we would get if we were to use the BBEP, the biomass burning product emissions that Talat described before, you definitely get at most sites a stronger association between the PM and the permit data. And finally, just to put this into context, at many of these sites, that association between PM 2.5 and prescribed fire activity is actually stronger than the association that you would see between PM 2.5 and several meteorological variables or drivers of air pollution. So if we compare those PM 2.5 associations with the permits to different MET drivers, in this case, including things like wind speed, wind direction, temperature, precipitation, relative humidity, things we know that can have an impact on air quality, we actually find a greater influence of the prescribed fire activity on the observed PM 2.5, especially at sites in Georgia and sites that go further away from the coasts. So around the coast, you can still, at many sites, you can still see a bigger impact or a bigger influence from meteorology, but as you move inland and move into Georgia, the influence tends to be stronger for prescribed fire compared to some of these known MET drivers. Okay, and in the next slide, just some additional observations from analyzing air quality and prescribed fire data. At most locations, the influence of prescribed burning that we were able to detect this analysis on local PM 2.5 persists for about 48 hours. For example, the figure here on the right is showing how the number of sites with a significant association between permitted fire activity and PM 2.5 drops as you move past kind of beyond 48 hours prior to the observation. So the figure shows that the highest associations and the highest number of air stations showing a significant association happens when you try to associate PM 2.5 observations and the amount of fire, prescribed fire permitted the day of the observation and the day prior to that observation. So about 48 hours. And if we look at how that association between fire and local PM 2.5 extends spatially, and you would see that at many locations, you'd find that maximum kind of radius of influence for prescribed fire on local PM 2.5, somewhere between 20 or 60 kilometers from the site, although this is not as consistent as kind of the timing of the fires. Many sites are located near coasts or sometimes near the edge of a state where we don't have prescribed fire data to begin with. So, but in general, that association, we tend to find the maximum somewhere between 20 and 60 kilometers. And we've also looked at these associations across multiple years and found that if you look at individual years from 2013 to 2016 at least, look at the burn seasons during these years, the associations are relatively constant. So you would find the same stations with the highest impacts from prescribed burning and a fairly similar influence of prescribed burning on PM 2.5 observations across at least these different years from 2013 to 2016. Okay, and one additional aspect that I will mention is that we have also been working to identify and characterize the communities where all this prescribed fire is occurring, and also trying to get an assessment of their vulnerability to smoke. So we've done some analysis to compare where prescribed fire occurs and where people may be more socially vulnerable or more vulnerable to smoke exposure. In this case, we're comparing kind of burn intensity, which we looked at before, specifically for the Southeast, Georgia and Florida. And as you can see, there's definitely some significant spatial variability in the amount of prescribed fire occurring even within these two states. But if we look at a metric for social vulnerability, then there's also some significant spatial variability across the state, with some regions, of course, being more vulnerable than others. In the next slide, we can see some of the information that goes into the social vulnerability index that we've been using specifically. So to characterize that potential vulnerability of communities to prescribed fire and smoke, we've been using the CDC's, the Center of Disease Control and Prevention's Social Vulnerability Index, which really tries to characterize the resilience of communities when facing external stresses on health, and does so by grouping different social variables across four main themes. There's variables that correspond to socioeconomic vulnerability, variables that characterize household composition, disability of the fraction of people with a disability within a community, minority status, and language, and housing and transportation access within these communities. So the vulnerability index ranges from 0 to 1, and we're using census tract data here for our vulnerability data as well as the burn intensity data. And what we find, and is shown in the next slide, is that at a state level, when you look at this region, communities in burn intensive regions tend to have higher social vulnerability. So if we focus, for example, on the state of Georgia, the social vulnerability for the 10% of census tracts with the highest burning intensity tends to be about 33% higher than the vulnerability for the rest of the states. But these census tracts that correspond to the top 10% by burn intensity, 12 out of the 15 variables that compose this social vulnerability index are higher. Some of the variables driving this increased vulnerability are mainly things like the fraction of the population below the poverty line, the fraction of civilians with a disability, fraction of population to 65 years or older, some differences in housing, the percentage of the population living in mobile homes, the different factors contributing to this higher vulnerability that we observe near in the communities near burn intensive regions. And finally, in the next slide, if we look at the spatial distribution of social vulnerability and burn intensity, instead of looking at kind of the statewide numbers, if we look at how these vulnerabilities are distributed and also look at local indicators of spatial association statistics, we find that there are clusters of prescribed fire activity and social vulnerability, and about 15% of the total area in Georgia and Florida has spatial clustering of high social vulnerability and also high burn intensity. Specifically, you can see these hotspots kind of concentrated in southwestern Georgia and northwest Florida, as well as south central Florida. So in these regions, you would find communities that have high vulnerability and also are close to the areas with the highest level of prescribed burning. And finally, in the next slide, if you can draw a few observations at these locations as well. One is that some of the air quality monitoring sites near these hotspots are also some of the ones with the strongest associations between prescribed fire activity and air quality. But the observations or the sites around these hotspots are fairly scarce. So generally, there are more monitors located in cities like Atlanta or close to cities like Jacksonville or Tampa or Miami than monitors located within these hotspots with the higher social vulnerability and also the higher burn intensity. So we've been including some of this information about demographics and vulnerability of population into the analysis that we've been doing, and we'll also include it into the system that Talat will talk about next. So I'll pass it back to Talat, who's going to talk about the system that integrates some of this data, as well as some air quality forecasting and fire forecasting, and which will be the focus of the demo he'll do towards the end of this presentation.
So before I can demo the SIPFIS, I want to show you one important component. So if you recall, our objective was also to include simulations, model simulations that will tell us more about the exposure to smoke, to prescribed fire smoke. And the way we do that is by including predictions from our operational forecasting system. Now, this is something we have developed with funding from Environmental Protection Agency. So we have done this for Georgia since about 2014. And now we continue the operation with funding from the NASA Health and Air Quality Applied Sciences team. And we are expanding, the forecast, both in terms of the geography. So we have extended it to the rest of the Southeast. And we are also adding new features such as the health impacts. So what we do is we put out daily forecasts of air quality and also the prescribed burn activity, as well as the impact of that activity on air quality. So it's like maps that you see here. So this is a PM 2.5 forecast, including the burn impacts. And this is just the portion or the contribution of the burns to that PM 2.5 concentrations. So we distribute these forecasts through our website at this address. So if state agencies and state air quality and forest agencies are interested in this forecast, they can take a look at it, see what level of activity we are predicting for the next day, and what the impact of that activity would be on air quality. So if they don't want to cause any air quality issues at downwind urban areas, they can use this forecast as a means to manage the permits that they issue the next day, for example. And the extension that I've mentioned is going to be related to exposures. So we are doing this for CDC and its partners for public health tracking, and also for epidemiological assessments specific to the prescribed fire smoke. And this is the address to CDC's public health tracking network. We hope to provide them with the prescribed fire information. They currently have information related to wildfires. And the forecasting system that we have developed has been described in this article that showed up recently in Atmosphere. Now, Atmosphere is an open access publication, so you can all find this and read more about the details in there of how the system works. I just want to briefly highlight some of the features. So the burn activity forecast is based on the weather forecast and the historic burning patterns. As you all know, weather has a strong influence on your decision of whether to burn or not to burn. So for instance, if it's going to be rainy tomorrow, you're likely not to burn. Or if the winds are going to be very strong, you're not going to burn either. So we use the relations between weather and burning patterns in the past and build a decision tree model, which we then use together with the weather forecast, and we predict the activity. So what you're seeing here in the middle, the blue dots are the burns that we have forecasted for a particular day back in March 13th of this year. Notice that we're not only forecasting for Georgia anymore, we are forecasting not for the entire states around them, but at least for the portions that are shown in this domain. And then one thing that we do daily is to compare our forecast to the satellite fire detections the next day. So NOAA's hazard mapping, which is essentially the basis for the biomass burning emissions product that we have mentioned earlier, they put out these fire detections the next day. So we have a chance to compare our forecast and see how well we did. On this particular day, we predicted high burn activity in southwestern Georgia, and that actually happened according to the satellite detections. And then we also, this is a qualitative comparison, the comparison with the HMS 5 detections, but we also have a quantitative comparison, which we'll later do once we get the permit records from the state agencies. And here you're seeing a comparison of the state total acres permitted versus forecast. So these are the ways by which we're trying to build confidence for our burn activity forecasts. And if you're interested in the details, the weather forecast is done with the WRF model. So the burn activity forecast gives us the number, location, and size of the burns. Then from that, we are using a blue sky-like framework. I shouldn't actually say blue sky exactly, because over the years we have diverged from blue sky. But we are using the fuel loads for the locations where we predict burns. And we are also predicting how much of that fuel would be consumed, and using emission factors that we have developed for the Southeast. We are calculating fire emissions, and also we are calculating plume rise. And then we combine these fire emissions with emissions from all kinds of other sources, including power plants, industrial sources, highways, and so on, because all those emissions will interact in the atmosphere. And then we use the community multi-scale air quality model to run an air quality forecast. And the direct decoupled method for sensitivity analysis allows us to calculate the fraction of the air quality or the contribution of prescribed fires to the air quality. And we are disseminating these products, which are actually forecasts. We are feeding these forecasts later to the information system, SIPFIS, and we are disseminating these predictions via a WebGIS-based system. So the next thing that I'm gonna do is take you to the live SIPFIS website and show you how, well, at least one way of how the information on the website can be used for your analysis. So this is the registration link that you all got to get to this webinar. So I just wanted to point out that there is a live link there to the website. So I'm going to use that. And here we are at the SIPFIS website. So I recommend that you start by reading the About page. So it tells you what SIPFIS is, and also tells you what information is available. So if you are trying to find something that we don't have, reading this page can avoid a lot of frustration. For example, for the permits, we only have records for Florida and Georgia from 2015 to 2016. So don't try to find any burn permit records in another state for 2017 or in these, not even in these states, Florida and Georgia. So let's come back to the home. Now, as soon as you get here, the map defaults to yesterday. So you're looking at October 4th here. So what I'm going to do is to take you to a different day, the day from the past. So you can type in the date that you want in this box. And then now it's displaying that day. Now we have two types of, by the way, there's also a calendar here. So, you can use the calendar to go to a different day on the same month easily here. So we have, the default is PM 2.5, but we also have data for ozone, if you want to look at ozone. So let's put the PM 2.5 observations for that day on the map. By the way, this map, by default is centered around Atlanta, so you can move it to where you want to look at. And you can also zoom in, zoom out. I'm doing this by using the roller on my mouse now, but you can certainly use this button here. So let's take a look at what happened near Columbus, Georgia on that day. And now there is also this portion of the screen where we can look at the time series of polluted concentrations. This has both ozone and ozone is orange and PM 2.5 is blue. So the points are the observations, and notice that as I'm hovering my mouse over these points, it gives me the values. So it's a little bit too busy, so I'm gonna take out the ozone. So you can do that by clicking on the orange points and lines. So what we are left with is, since we were interested on March 10th, we have the daily average concentrations, and this is, by the way, still focused at an Atlanta site, Confederate Avenue. So if we are interested in Columbus, what you can see, you can hover over Columbus and it's going to tell you the daily average PM 2.5, right? But what you can do, you can click on that site, the marker for the site, and you get the time series for that site. So once again, let me disable ozone so that we can focus on Columbus. So now 12.3 on the map and 12.3 here. Now the line is actually the result of our forecast on that day. So this is the value that we have forecasted, but without any burns. So as you can see, the forecast is 6.1, the observation is 12.3 micrograms per cubic meter. There's a difference of about 6 micrograms. So we're gonna try to analyze that. And by the way, this bottom window, let's disable ozone again. It's showing the hourly concentrations for the week preceding the day that we're interested in, which is March 10th here. So we can see, what the concentrations have been on previous days. So now the next thing that I'm gonna do is close this window so that we can focus better on the map. And I'm gonna put the predictions. So we call them predictions here. But I want you to remember that these are actually forecasts that we have produced on one day prior to this, on March 9th. So that would be the latest one. And actually our forecast is it extends 3 days from the day that it's produced. So we also have a forecast that was produced on the 8th, on March 8th, and another forecast produced on the 7th. And unfortunately, that day something must have went wrong, so we don't have a forecast for that day. So let's come to the latest one, because that's it's our expectation that the closer you are, the more accurate the forecast is going to be. So if you look around in Georgia, everywhere we have predicted good air quality, PM 2.5 levels less than 12 micrograms per cubic meter. But the observations, are showing several monitors that are above 12 micrograms per cubic meter, including these 2 sites in Atlanta. So now we're going to try to analyze why that may be. So I'm going to put the burn predictions on the map. So these are, this is the product of our burn activity forecast. So as you can see, we have been predicting, fires south of Columbus, and as well as, south of Atlanta. Now let's take out the PM 2.5 forecast and bring in the satellite detections. So these are the locations of the fires that the HMS product has detected the next day. So you can compare our forecast to the satellite detections. In terms of locations, of course, there's no way to predict the exact location of a fire that's going to happen the next day. But in terms of the density and the locations, there seems to be quite good agreement, on this day between our forecast and the satellite detections. Now, I can also compare this forecast to the permits. So you can see, for example, that right here, there is a rather large burn, and we did forecast a 200-acre burn right here, and there was actually a permitted burn for 250 acres, not too far from that. Okay, so now the next thing that I'm gonna do, let me also disable the permits and bring in the burn impact. So this is what we do with the air quality model, what we predict with the air quality model. So for these burns that we have predicted, the impact near Columbus, not right at Columbus, but very near to it, it's about 2 to 5 micrograms per cubic meter. And similarly, this cluster of burns will have an impact of about, once again, 5 to 10 micrograms at these two Atlanta monitors. So now let's go ahead and look at the air quality prediction with burns. So we add the contribution of the burns to the air quality that we forecasted. So now you can see that it's no longer green everywhere. I mean, we forecast or predict moderate air quality, that is between 12 to 35 micrograms per cubic meter at various locations, not at the monitors in particular, but near to them. So as a forecaster, for example, I would look at this, and when I produce a forecast, I would consider the likelihood that, you know, these burn clusters may be closer to the monitors, or, you know, there may be some uncertainties in the forecasted wind directions. So I may tend to issue a moderate air quality forecast for this day, given the burn activity and how the winds would be blowing from the south. So now let me go back to the presentation and point out another feature here. So we looked at this. This was the comparison of the permits with the burns that we have predicted. Notice that there was a permit right here for a large burn, actually larger than 150 acres, which we did not forecast. And then recall that, you know, this cluster of burns, they had an impact of about 10 to 20 micrograms at a similar distance between, you know, this permitted burn and Atlanta. So given that information, it's likely that, you know, these moderate PM 2.5 levels at Atlanta on that day were caused by this rather large burn here. Okay, so let's leave it there and just switch to what's coming. So this is something that we are working on right now.
Talat, can you go back to presentation mode for your PowerPoint?
Thank you.
Yep, thank you.
I forgot to do that. So we're working on this with CDC. Now, this is a typical concentration response function. We have concentrations of PM on the x-axis and a response, in this case, in asthma emergency room visits. So as you can see, for high PM 2.5 levels, or as PM 2.5 increases, people show up more at the emergency rooms due to asthma attacks. So we are using these health burden functions to produce maps that take our PM 2.5 forecasts and turn them into a burden in a base health rate. For instance, this is again for asthma ER visits. And these numbers are in percentages. So wherever you see a red point, for instance, on this day, you can expect a 40% increase in the number of people who show up at the emergency rooms. So these are also going to be part of our forecasts, and they will be archived in the SIPFIS website. At this point, let me summarize. So we have asked for your data, and let me do it one more time, because SIPFIS is still evolving. We've got more time to include your prescribed fire data in the system. Permit data is being integrated with air quality and demographic information, as Fernando shared with you. And we are assessing the prescribed fire impacts in the region, in the southeast in particular. Now we have developed a forecasting system that predicts the impacts of prescribed fire on air quality. And let me remind you that we have just published this this paper that details how we do the forecast, and recently we expanded the forecast to other states. So you may want to watch the daily forecast that we put out, just to see, if you feel comfortable. By the way, I failed to mention that, the data that we use to build the decision model, it's permit-based only in Georgia. For other states, we are using satellite-based data. So, and it's fairly recent. So it's not going to be as accurate in other states as it is in Georgia. And then again, this is the link to the SIPFIS website. So this tool has the data that we have. It has all of it, and we update it daily with the new data coming in. And we are extending, our database with fire impacts that including human exposure and health burden forecasts. So we are hoping that SIPFIS and the HiRes-X forecasting system will benefit air quality, forest, and health service agencies in the Southeastern U.S. So thank you very much. And these are our emails. You can contact us anytime you want. And we would be very pleased, if you send us comments on the SIPFIS system, as well as share your data with us. Thank you.
All right. Thank you, Talat, and thank you, Fernando. Once again, if you all joined us during the presentation, my name is David Godwin, and I'm the coordinator for the Southern Fire Exchange. And the presentation we just saw was by Dr. Talat Odman of Georgia Tech and Dr. Fernando Garcia Menendez of NC State University. I know we're past the 2 o'clock hour, but we already have some questions that have come in, and I want to see if our speakers can take some time to address those before we leave today. If you guys have any other questions, you can put them in the Q&A window or the chat window, or since we're running up over time already, you might want to go ahead and email our speakers directly. You can see their email addresses on the screen, but we'll go ahead and see if we can get through some of these questions that have already come in. So one of the first ones that we had came in from Lucas, and he's asking if the model integrates national fire occurrence data from other programs such as land fire, or if only state level permit data and occurrence were pulled in along with satellite imagery. So do you have any other inputs that feed the system in terms of fire occurrence?
No, essentially it's just the permit data from the states that were listed in Fernando's first slide, and also some data from tall timbers.
Mm-hmm. Okay, I think this ties into another question that came in from the Q&A just a moment ago, and this person says, I assume prescribed fires are permitted and planned before the burn occurs. Why then do you need to predict the prescribed fires? Why not integrate the system with land managers to base forecast? So I think they're getting to, do you have the ability to pull in permits on a daily or real-time basis from the states, or do you see that as something in the future that might be a feature of the system?
Well, it could be done, though it would be difficult, because the permits are typically, at least in Georgia, they are typically issued the morning of the burn. So by the time the permit is issued, it's a little too late for us to run a forecast. And plus, the real benefit of the forecast is for the agency that is issuing the permits to see the situation on their screen. So we prepare the forecast the day before, so when they come in and start taking applications for permits, they have it on their screen, so they can look at the level of activity that we have predicted, and they can look at the actual phone calls coming in, so how well those agree, and then they can look at the impacts, air quality impacts that we have forecasted, and if they choose to do so, they can actually manage the number of permits that they issue so that they don't cause any air quality issues at downwind cities, urban areas.
So with those modeled, or I guess predictions of where the prescribed burns are going to occur, this ties to a question that just came in. Have you guys done any analysis to assess the accuracy of those predicted burns versus those that were actually permitted or detected?
Yes, as I mentioned, we have two types of evaluations for the burn forecasts. One is qualitative, and it's essentially a comparison of the fires that are detected by satellite, with the location and number of fires that we forecast. And the second level of evaluation is quantitative, so that's based on the permit records, which we do afterwards once we get the permit data from the states. And the paper that I mentioned, the atmosphere paper, has more on the evaluation.
Mm-hmm. Okay, so for folks who are interested in that, I pasted a link to that atmosphere paper in the chat window. And as you said, that is a open access publication, so anyone should have access to download that. So here's another question, and before we jump off of that, actually, I have my own question of, if it seems to me that it would be pretty important to be able to differentiate the differences in terms of air quality impacts and contributions between prescribed fires and wildfires in the Southeast, because that again is kind of the big question when it comes to forecasting and understanding the impacts of prescribed fires is how do they compare to wildfires. So if you're using this HMS system for satellite detections, do you have the ability to make that differentiation?
Well, no, we don't. So the satellite, it cannot tell whether it's wildfire or prescribed fire. But we have the ability to look at the permits later on and see, if there were. Actually, we also get wildfire records from the states, and so we have means of later on digging into that data and looking at which ones were wildfires, which ones were prescribed. But as I said, the satellites have major issues, major deficiencies in detecting the prescribed fires. That's what we have shown in the JGR article. And I should add that there is a new generation of satellites out there. Our analysis did not include any data from the recent GOES-16 satellite, for instance. Now NOAA is using GOES-16 data, and this evaluation has to be redone, for the current year. I believe they started getting some data from GOES-16 last year, but it's only this year that the data is blessed. So we need to do this evaluation again for 2020 for the coming years.
And John Cook gets the last question of the afternoon, and he put this in the Q&A window, and he says, are the forecasts based on 24-hour averages, EPA of emissions, or 3-hour based on U.S. Forest Service, or according to U.S. Forest Service? So are they 24-hour averages or 3-hour averages?
Well, we have the ability to forecast hour by hour, but of course we make some assumptions about the start time of the fires. For instance, we start them all at 11 a.m. But then from there on, we are able to track PM 2.5 hour by hour. The results that I shown were converted to daily averages, just because that's the metric that air quality agencies are interested in. But we have the data. If 3-hour averages were needed, we could produce that.
Well, great. Well, thank you very much for joining us today, and thank you for the questions that we had that came in from folks on the line and in the chat window. And it's a fascinating system. If you guys have questions for Dr. Odman or Dr. Menendez, again, their email addresses are on the screen. And if you would like to work with them and provide some data as they've requested on burn occurrences in the Southeast, please definitely consider shooting them an email and working with these guys on this project. As we've said, we've run up to the end of our time today. Thank you so much for joining us, everybody. As we close out the webinar, it should open up a window in your browser with a 5-question or so questionnaire, and let us know your thoughts on the project, and we share those results with our speakers. And we also use your feedback to improve our future webinars to meet your fire science needs. As we said at the beginning, the webinar was recorded, and that recording will be on our YouTube channel in a couple of weeks. So thank you all for joining us today. Thank you, Dr. Odman, and thank you, Dr. Garcia Menendez, for joining us. Enjoyed your presentation, and have a good afternoon.